Oh, go ahead. Here you are. Does this seat work? No. Too bad. Welcome back, everybody. Homework 2 is available from the class webpage, so you can start that anytime you want. It will be due 16 days from today, so 2 weeks after this Wednesday. Homework 2 has sort of a special purpose, which is to help you figure out if you're mathematically prepared to take this class. It is the one assignment this semester, the programming project. It's all just math. As I've said before, there's certain things that you need to have a pretty good understanding of to survive this class. Linear algebra, probability should be strong, knowing what gradients are. And so homework 2 is going to sort of test you on this. Homework 2, you should expect it to be hard, but you should expect it to be doable if you have enough time and give it enough time. So please get started early. It's a long one, deliberately so. Again, it does have the purpose of helping you decide whether you are prepared for this class. So, if you find it difficult but you can do it, you're good. If you find that there's swaths of material where you just don't even know where to get started, you might want to ask whether you're ready for this class yet. And I do need to point out that there are still several hundred students on the wait list who would be very, very grateful if you decide to drop the class. So, again, not trying to discourage anybody, but if you're not ready for the class, it's healthy if you realize that in time. And not coincidentally, the homework 2 due date coincides with the final day for dropping classes. All right, so let's get down to more about classifiers, especially today, linear classifiers. We need to learn some of the basic terminology surrounding classifiers in machine learning. So we begin by assuming that are the speakers flaky? Are they going in and out? Yeah, afraid of that. I hope that's not happening on the recording. I'm not sure what is causing it or what to do about it. You're given a sample. So an observation is some sort of data taken from the real world, and each observation has D features, or quantitative values associated with it, and sometimes features are also called predictors, but this semester we'll always call them features. To the feature, we're told that we're given labels saying that some observations belong to a class C. Some other ones do not. So continuing on a theme very similar to last lecture, suppose that the observations are bank loans, and we have two features, income and age. So we're going to say D is equal to 2. D is always the number of features in our model. And some of the observations are in the class that we call defaulted, people who have defaulted on their loan. There's another mic in here. I'm going to try this one to see if it's more reliable. Seems to be working. Pardon the noise. This one's a little more echoey, but I hope it will stay working. We have a goal in all of this. This one's definitely louder than the other one, so I guess I can turn it down. Our goal is prediction. In this case, we want to predict if future borrowers are going to default, given their income and age, but no label to tell us in advance what's going to happen. So the data we want to predict on is unlabeled. The data we trained on is labeled. Now, in machine learning, we almost always think of each data point or each observation as being a point in a d-dimensional space. Which is easy when it's a two-dimensional space and hard when it's a million-dimensional space. But these observations, since we're thinking of them as points in some Euclidean space, we might call them sample points. But they go by other names, so these are synonyms that you'll often see in the literature as well. You might see a reference to something called a feature vector. That's the same thing. That's a sample point. And of course, in certain contexts, they're referred to as the independent variables of the problem. And then the thing you're trying to predict is the dependent variable. So to make this a little more visual, let's consider 3 different examples of possible data sets we might get. X-axis is age, y-axis is income. So the first possibility is going to be the easy case. Maybe those are my sample points in class C, and here's a bunch of sample points that are not in class C. That one's easy. The next 2 will be less easy. So in my second example, which could happen, you might wind up seeing something kind of like this. And one more example. In this one, it kind of looks like there's no structure at all, and maybe there isn't. These could be random for all you know. So, in each of these 3 cases, what we're going to do when we do machine learning for classification is to try to draw some sort of decision boundary that separates the class C from the not class C, or at least separates most of them. And so, obviously in the first example, we can do that with a linear decision boundary. We can get 100% training accuracy with a linear decision boundary, meaning that we can create a linear classifier that correctly predicts everything on the left of the line is a C, everything on the right is an X. That is correct for all of the training points. Might not be true for all of the points you'll predict later, but it's nice. In the second example, of course, that's not possible, but we still see what looks like a pretty reasonable decision boundary. It's just not linear. There are problems where linear decision boundaries work great, and problems where they're just not flexible enough, and they don't work great. And in this third example, well, you can draw a decision boundary if you want to, but do you really trust this decision boundary? That decision boundary is probably overfitting. And overfitting usually means that our predictions aren't likely to be very good. So the ability to get 100% training accuracy doesn't mean anything, really. You could still have a terrible classifier. So just a reminder, I defined decision boundary last class, and it is the boundary chosen by our classifier for the sake of prediction. And it separates items that are in the class from those that are not. But unlike the decision boundaries I've drawn there, they don't always have 100% training accuracy, because sometimes it's better to sacrifice training accuracy to get better test accuracy. And the third example is an example where that happens, and we believe that that will probably lead to overfitting, which is when you make your decision boundaries so sinuous that it's unlikely that they correspond to an understanding of the reality of the situation. So when you overfit, you tend to make bad predictions. Now, there are many, many different ways to create classifiers and decision boundaries, but quite a few of them work in the following way, but not all do. They compute what's called a decision function. So let me define decision function. The idea of a decision function is that we're going to define a function we'll call f that is defined over the whole feature space, the whole d-dimensional Euclidean space of our sample points. And that function maps every point in the space to some scalar. And the scalar value produced by f is, if it comes out positive, then we are predicting that any point in that location is more likely to be in class C than not. And if f of x is not positive, then we're going to predict that x is not in class C. These decision functions sometimes go by another name. They're also called predictor functions. And by the way, we made a somewhat arbitrary choice here about what happens when f of x is exactly equal to 0. In many contexts, it doesn't really matter which way you go when f is exactly 0. You know, we could have put a greater than or equal to here and a less than here. Whether or not you should do one or the other may depend on your application, but often just doesn't matter at all. So if we have a classifier that uses this kind of decision function, then it's easy to at least mathematically express what the decision boundary is. Working? Okay, I think the battery went dead on that one. So again, for classifiers that use a decision function, the decision boundary is the set of all points in our d-dimensional feature space such that f of x is equal to 0. So the set of all points where the decision function is 0 is your decision boundary. Usually, although not always, this set is a surface, or specifically, topologists will say that it's a d-1 dimensional surface in d-dimensional space. I'll show you a few visual examples in a minute, but before I do, let me point out that this set of points where f is 0 has some other terminology that sometimes you'll hear. This set of points is called an isosurface of the function f. And for a specific iso value, namely 0. So the 0 surface is one isosurface of the function f. It's not generally the only isosurface of f. F will have many different isosurfaces, one for every scalar value you can think of. So, I mean, we can talk about the set of all points where f of x is equal to 1, and that is also an isosurface. It's just an isosurface with iso value 1. And there will be times in this course when our decision boundaries will be isosurfaces whose iso values are not 0. But today, the iso value will always be 0. So let me illustrate this a little bit. Here is a simple example in a two-dimensional feature space of some isosurfaces. So what are we looking at here? The left figure and the right figure are two different ways of depicting exactly the same function f. So they're not different. They're the same function viewed two different ways. And so the idea is that your feature space has two entries. x1 is this axis, and x2 is that axis on the left. And then this is a 3D plot, obviously. The vertical direction is f of the vector x. So that's a 3D plot of that function, which kind of looks like a cone. On the right-hand side, again, the horizontal axis is the first feature, x1. The vertical axis is the second feature, x2. But now we are showing what's called a contour plot, which shows you the isosurfaces of that function, or some of the isosurfaces. In particular, you'll see there's a little 0 here. This is the isocontour where f is equal to 0. So that could very plausibly be a decision boundary in your algorithm. But this function has other isocontours as well. And as I said, there are circumstances where a different isocontour might be the best one for a particular machine learning problem. Maybe f of x equals 2. In this case, the isosurfaces are essentially just loops, like pieces of string. So topologists see them as a one-dimensional object, each isosurface here. And so they're usually called isocontours in the special case of a two-dimensional function with one-dimensional isosurfaces. But usually when we do machine learning, we're going to be doing a lot more than two-dimensional or two features per sample point. So you need to try to learn how to visualize this stuff in higher dimensions. And so that's harder, but at least we can go to 3 dimensions pretty easily, or a 3-dimensional feature space, that is. Here's an example showing a bunch of different isocontours of a 3-dimensional decision function. Questions about that? On the far right? Yeah. The term level set is often used as a synonym for isosurface, yes. Though, I mean, the word level set has some extra baggage that isosurface doesn't have, which I'm not going to go into. Okay. Other question?
So my other question was, is using a decision function for classification purposes, is that essentially the same thing as using like an SVM, but like having features that like correspond to like, you know, x squared, x cubed, like higher order terms?
Well, you ask if using a decision function is like using an SVM. So 2 things to say there. One, there are lots of decision functions that are very different from SVMs. And two, SVMs don't actually use a decision function. They are a linear classifier, they give you a linear decision boundary, but they don't get there through a linear decision function, or through a decision function at all. Well, we'll find out over the next couple of lectures. Sorry, I can't answer that yet, but we'll get there. Other questions? Yes? Of course not. The lines are not always circular, no. They could be almost any shape. We'll see lots of shapes of decision boundaries throughout the semester. Here, yes.
How can we calculate the dimension for the isosurface? Because I mean there are two features, and according to the d minus one dimension, the curve should be one dimension.
Mm.
But I do not think the general curve is always the one dimensional either.
Right, the general curve is not always one-dimensional. There's even an example right here. If you choose exactly the right isocontour of the function here, then you will discover that just a single point here, that is an isocontour, but it's not one-dimensional. And in general, you can have pathological-looking isocontours with things like that, and much more complicated than that. There's a whole field of mathematics called real algebraic geometry that tries to answer questions like, how do you know if a surface has a certain shape? But when we're doing machine learning, we essentially never have to worry about that. We rarely explicitly construct the decision boundary unless it's very simple, like linear. Mm-hmm. Yes?
According to the predictor function, you said that we can, if f had the iso values might not be zero. So can I just change like take gx equals, for example, if its iso values is 1, so can I just take gx equals to fx plus 1?
Can you get another iso contour by saying gx equals fx plus 1?
I mean the predicted the isosurfaces, it might we can just say that its iso values is 0. We don't focus on the values because we can always take another.
Oh, right. You can always, if you're looking at an isosurface with an iso value of 3, you can always define a different function where it has the same isosurface, but with an iso value of 0. Yes, that's easy. Mm-hmm. Yes. Oh, when do you want a non-zero iso value? Is that what you're asking? Well, the first example of that we'll get a look at is, I'll give a brief bit of attention to that when we talk about Gaussian discriminant analysis, which is one of the algorithms we're going to learn in this class. And Gaussian discriminant analysis, for reasons I'll explain in about 2 weeks, you often want to change the probability with which, you want to not necessarily have a classifier that's correct at least 50% of the time, because like in a medical situation where you're trying to decide whether to do surgery on someone or not, you might want to err in the direction of safety. And so instead of having a classifier that just tells you which class is most likely to be true, you weight the iso contour, you weight the iso value so that you get a risk benefit trade-off that's not one-to-one. Mm-hmm.
Why the isosurface is d minus 1 dimensional surface? Like for 2-dimensional, I know like we see from the picture like there's
Mm-hmm.
a line to separate, and for 3D dimensional we see from 2D dimensional. But for higher dimensional, how would you prove that?
Why is it d minus 1 dimensional? Well, you can't prove it because it's not always true, but the intuition I want you to have is that there's a big chunk of space where f is positive. That chunk of space is usually d-dimensional. There's a big chunk of space where f is negative. That chunk of space is also usually d-dimensional. And then there's somewhere where they meet. And because it's where they meet, it necessarily is d minus 1 dimensional, or lower. The or lower part is a trick that we're not going to get into in this class. Well, I gave this example right here of an isocontour that's just a point and not a circle. That's about as far as I want to get into that topic. It's very hairy. Other questions? Mm-hmm. And that's a good question. Do decision functions have to be continuous? No, they don't. They don't. Usually they are, but not always. We're going to see some algorithms this semester, like decision trees, where you get a very discontinuous result. So sometimes that's useful for some applications. One thing I want to add here is that a lot of the classifiers we learn this semester will be linear classifiers. We're also going to learn a lot that are not linear classifiers, so don't worry. But what makes a linear classifier is that the decision boundary is, well, in two-dimensional feature space, it's a line. In three-dimensional feature space, it's a plane. In a higher dimensional feature space, it's what's called a hyperplane, which we'll talk about in a minute. But before we get there, I just want to say that a lot of the linear classifiers, maybe most of them, use a linear decision function to get to the linear decision boundary. But there are some very big exceptions, most famously support vector machines. Do not have a decision function. They just go straight to a linear decision boundary. So before we get to more details, I want to walk you through a little bit of math, hopefully mostly math that you've seen before in some form, but just to clarify how we think about things in this class. So I'm always going to write vectors in matrix notation. And so in this class, the vectors that we care about will almost always be column vectors rather than row vectors. There might be some exceptions to that, but not very many. And so I write this one as a 5x1 matrix, the vector. You could also, for brevity, write it as a 1x5 matrix and then throw a transpose at the end of it. And so when you see that, we are thinking of X as a point in 5-dimensional space. Again, I know 5-dimensional space is hard to think about, but a lot of the intuition you know from 3-dimensional spaces will transfer pretty easily. Now, in the hopes of helping you through the thicket of notation that comes along with machine learning, I have at least structured my lecture notes so that I try to follow certain conventions most of the time. Unfortunately, there will be times when I have to break with these conventions, but when I can do it, I will try to make the letters give you a hint about what their structure is. For instance, when you see an uppercase Roman letter, that usually refers to either a matrix, a random variable, or a set, depending on context. So a typical example would be capital X will be our design matrix of sample points throughout this semester. If I use a lowercase Roman letter, that's usually a vector. So when you see a little x, that's probably a vector. When I can, I'll use Greek letters for scalar values, like alpha. But there are some other scalars that will come up a huge amount. And so one thing I'm going to stick to is throughout the whole semester, n will only ever mean one thing. It's the number of sample points. I don't plan to ever use n to mean anything else. And likewise, d will always mean the number of features per sample point, which you can also think of as the dimension of the sample points. And of course, following standard usage, I, j, and k will usually be integer indices. And then functions will come up a lot in this course. Often the functions are scalar, but not always. It's very hard to enforce a particular notation for that for various historical reasons. But for example, f and s will both be used mainly for functions. You're probably all familiar with vector inner products, which are also known as dot products. But just to familiarize you with the notations we'll use, there are several different notations we might use. One is a dot, x dot y is the vector inner product. But sometimes, depending on context, we'll prefer to use matrix notation to write that inner product. So sometimes you'll see it written x transpose y. And again, the reason it's x transpose y is because x and y are going to be virtually always column vectors, not row vectors, because that's our convention. So with this in mind, it should be clear that if I write the following function, f of x equals w dot x plus alpha, which, well, that is a linear function. Specifically, it's linear in x. And the reason I'm writing this particular function down is because that's going to be the decision function for quite a few of our linear classifiers. You all should also be familiar with the Euclidean norm. When you see a norm operator in this class, it's generally the Euclidean norm unless otherwise specified, which is the square root of the inner product of x with itself. And so we say that the Euclidean norm of x is the length of the vector x, for short, though you probably know that mathematicians like to use more than one kind of length, so to be explicit, this is called the Euclidean length. And if someone gives you a vector x, and the vector is not 0, then x divided by the length of x is always going to give you a unit vector, meaning a vector whose length is 1. And so you'll often hear the phrase normalize a vector. And usually, well, the word normalize is a little bit fuzzy. It's used in multiple ways by multiple people. But most commonly it's used to refer to the act of replacing x with the unit vector pointing in the same direction in some algorithm. So once you've got dot products defined, one of their useful purposes is to compute angles. And so if I have a vector x and another vector y, and I want to know the angle at which they meet, then there's a standard formula for this, which is that the cosine of that angle is the inner product of x and y divided by the length of x and divided by the length of y. And if you pull this apart, you'll notice that this is really an inner product between two unit vectors. That's how I remember it anyway, is that it's really, this formula is really referring to just the inner product between two unit vectors pointing in the appropriate directions. And sometimes we're interested in the difference between acute angles, right angles, and obtuse angles. So an acute angle, one where the angle is less than 90 degrees, is characterized by the fact that the inner product of x and y is positive. And a right angle, if I can draw one, is characterized by the fact that the inner product is 0. And an obtuse angle is characterized by a negative inner product. Obtuse meaning the angle is greater than 90 degrees. All right, coming back to our linear decision function. If your classifier somehow learns a linear decision function of the following form, w dot x plus alpha, then the decision boundary can be written as the following point set. I'm going to call the point set capital H. It's the set of all points in d-dimensional feature space such that the inner product of w with x is minus alpha. So the reason I used the letter h is because this set of points, h, is called a hyperplane. So again, if you're working in a two-dimensional feature space, hyperplane is just another word for a line. If you're working in a three-dimensional feature space, a hyperplane is just a plane. But if you're working in a 1,000-dimensional feature space, then your hyperplane is going to be 999-dimensional. So a hyperplane is just what you get when you generalize the idea of a plane to higher dimensions. And there's basically three things you need to understand about them. The first is that a hyperplane in d-dimensional space has dimension d minus 1, and it cuts the space into two pieces. Secondly, hyperplanes are flat. Third, they're infinite. They go on in some directions forever. Any questions about any of this? Mm-hmm. Well, the decision function is itself a linear function in the basic algebraic sense. Oh, I see, okay, yes. Okay. There are axioms of linear algebra that aren't really relevant to what I'm saying here. Yes.
Is it when we always use these classifiers to kind of give you binary decision, or is it possible for us to kind of produce like two sets of?
Well, fine question. When we have what are called multi-class problems, where the decision is not binary, but you might have to pick between three classes, a decision function, one decision function alone is not usually going to be the right way to approach that, though it's very common to use two decision functions to approach that. There's a little bit of discussion in the textbook of how that's done, but it's not going to be a big emphasis this semester. In the back? Mm-hmm. Mm-hmm. Circles, so I mean, are you saying you think that circles should be dimension 2? Okay. To a topologist, a circle has dimension 1, and that's what I'm referring to in this context. A topologist thinks of a circle as just a piece of string, and it only has one dimension of importance, and the fact that it happens to be embedded in some higher dimensional space where it snakes around is not relative to it, or relevant to its dimension. So, sorry if you're not, I know that's a little bit of weird to think of this as a circle as being one-dimensional instead of two-dimensional if you've never taken a topology class. But for the purposes of what we're talking about, I need to speak topologically. All right, so one thing that's really easy to show is that if you have 2 points, x and y, that both lie on a hyperplane H with the formula above, then the vector w that defines that plane is at a right angle with y minus x. Or in other words, the inner product of w and y minus x is 0. And the proof is very easy. If you look at w inner product with y minus x, w dot y is minus alpha. W dot x is also minus alpha. So you're subtracting minus alpha from itself and you get 0. But the important thing to take from this is that w is at right angles with y minus x. Or to put it another way, w is orthogonal to any vector that lies on the hyperplane H. So, for that reason, w is called the normal vector of H, normal implying orthogonal. So what the theorem tells us is that the vector w is perpendicular to the whole hyperplane H. We use the word normal in that context. It's normal to H. So let's think about this visually for a second. Just in two-dimensional space, suppose I have a function, a linear decision function defined over two-dimensional space, and I look at what decision boundary I get, for instance, with isosurface 0. Well, maybe I get, this is my decision boundary, and this vector w is always going to be orthogonal to that decision boundary in a linear classifier. And so this decision boundary is the set of all points where w dot x equals 0. But if you choose different ISO values instead of 0, you could, for instance, instead get the decision boundary w dot x equals 1, or the decision boundary w dot x equals minus 1, or the decision boundary w dot x equals minus 2. And they're all orthogonal to W. Now, if W just happens to be a unit vector, then this expression, w dot x plus alpha, our decision function, also has the nice property that it's something called the signed distance from the point x to the hyperplane h. So what's a signed distance? Well, it's like the distance. It encodes the distance from x to the hyperplane h. But it could be negative, or it could be positive, depending on which side of the hyperplane it's on. The hyperplane has a negative side and a positive side. So specifically, it's positive if it's on the same side of the hyperplane h that W is pointing into, whereas it's negative on the other side. Moreover, it's pretty easy to see that the distance from h to the origin, that is, the origin of our coordinate system, is alpha. So that's what alpha encodes, is the distance to the origin if W is a unit vector. How do we know that? Yeah, thank you. Replace x with 0. If you stick 0 here as x, the origin, then you get alpha. So that's the signed distance. So alpha is 0 if and only if the hyperplane h happens to pass through the origin. Now, everything I just said, except for that last statement, is conditioned on W being a unit vector, but W does not have to be a unit vector for the classifier to work. A classifier can totally work fine for any length of W, because all we care about is the sign that we're going to get, and scaling W does not change the sign that we're going to get. So if W is not a unit vector, then W dot x plus alpha is not the signed distance. It's the signed distance times some positive real number, which is still going to give you the correct sign. So it still works as a classifier. If you actually want to get to the signed distance, you can always rescale the equation by computing the length of W. And if the length of W is not 1, well, you divide W by its length. You divide alpha by the length of W as well. You get an equivalent classifier that also gives you the signed distance. So when we want to learn a linear classifier that uses a linear decision function, that means we are learning the coefficients in the vector w, plus we're also learning a scalar value, alpha. Each of those values is called a weight. Like many things in machine learning, weights sometimes go by other names. So if you see the word parameters in a machine learning paper, it's probably just a synonym for weights. And specifically in the context of regression problems, they're often called regression coefficients. But all of these different names refer to basically the same thing. Anyway, that's why we call the vector W. It stands for weights. All right, another definition. Sometimes our data is linearly separable. Sometimes it's not. It's linearly separable if there exists a hyperplane that separates all of the sample points in class C from all of the sample points not in class C. So let's go back and look at the obvious examples that I've already given you. These three graphs, recall them. Well, the data on the left is linearly separable, and I've proved it by drawing the line that separates them. And the example in the middle, it's not linearly separable. You will not find a line that separates the x's from the c's perfectly, and the one on the right is really not linearly separable. Question? Yes. So what does distance from h to the origin mean? It means if you have a hyperplane h and you have your origin of your coordinate system here, then you essentially find the shortest distance between the origin and the hyperplane h, and you measure the length of that thing. That is the distance from the origin to the hyperplane. Yes? Why is it the sign distance? I believe you'll have a homework question that asks you to figure that out. So I think that's on homework too, if I remember right. So I want you to work that out for yourself, please. All right. We are going to investigate a few linear classifiers that only work for linearly separable data, which is, in practice is rarely what you need. But they're a good place to start pedagogically. We're also going to investigate classifiers that do a decent job even with data that's not linearly separable. And those are going to be much more useful in practice. But, of course, it's always important to keep in mind that if your data is not linearly separable, then a linear classifier cannot do a perfect job. It cannot get 100% training accuracy. You will have to misclassify some of your training points. But we're still happy if we can find a classifier that usually classifies test points correctly. So to make this a little more concrete, I've been talking about linear classifiers without actually giving you one. Let me just tell you the simplest possible linear classifier that I can think of. And it's actually a well-known classifier, sometimes called the centroid method. So the idea is that we're going to compute the mean of all the training points in class C. We will call that mean mu subscript C. And we're also going to compute the mean of all the points not in class C. I'm going to call the mean of all those points mu subscript x. Once you've computed those two centroids, it's very, very quick to get to the decision function. The decision function is this. So the first idea is that we are going to take the difference between the two centroids, and that's going to be our normal vector. So we want a hyperplane that separates class C from class not C, or call it class X. This vector from mu C to mu X will be perpendicular to probably a pretty good hyperplane. The other thing that I want to do is I want to make sure that the hyperplane, the decision boundary, passes exactly halfway between mu C and mu X. So the way that I can achieve that is by making the constant alpha equal to this thing here. So the idea here is that we choose this to be the midpoint halfway between mu C and mu X. And what we want is that if you substitute that value in for x, the whole decision function is going to be 0. That is what forces the hyperplane to pass through that midpoint. And so that's it. That's our decision function. And when you do this, the decision boundary will be the hyperplane that bisects the line segment connecting mu C to mu X. Now, this will all make a lot more sense, maybe if you see an illustration of it. So let's draw an example. Here's a two-dimensional feature space, and I'm going to have some points called C. Here, 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 and then throw one way over here. And a bunch of points called X. All right, so if I compute the midpoint of all of the points in class C, maybe I get that this is mu of C. And if I compute the centroid of all the points in class X, maybe I get that this is class X. Well, I guess I didn't draw it quite right. But, so this is going to be our normal vector. And since I didn't draw it quite right, I need to move these a little bit, because I want to give you an example where this doesn't work perfectly. And so once we've decided that those are the centroids of the C's and the centroids of the X, then the normal vector is going to be the vector connecting them, which means that the hyperplane itself is going to be the plane orthogonal to that normal vector that passes exactly halfway between mu C and mu X. I did not draw that very well, but there's a slightly better attempt. So again, this point here, that's the midpoint, exactly halfway between mu C and mu X. And so the centroid method will produce this classifier. And you'll notice it does not have 100% training accuracy. You might say, well, I don't like that very much, because obviously there is a linear classifier that gets 100% training accuracy, and this is not it. Nevertheless, there are certain circumstances where this might be a better classifier than the more obvious one that gets 100% training accuracy, like if your data comes from a Gaussian distribution. And we'll see why in about 3 weeks. For now, though, let me just say that in terms of training error, this is not the worst example I could have come up with. If you're in the mood for a relatively easy puzzle, pull out a sheet of paper and think of an example that has lots of training points where the centroid method misclassifies every point except for 2 of them. Any questions about that? Yeah. I don't, if you have non-equal numbers of data points, like let's suppose that there are 100 times as many points in class C as there are in class X, I would still choose the midpoint halfway between mu C and mu X. The fact that the data points are not equal in number or very, very unequal doesn't really change the algorithm. We don't do it by looking at the number of points. What you could do is you could like project all of the data points onto the normal vector and then try to find an alternative hyperplane that is also normal to that normal vector, but gives you better training accuracy. Like this green line actually only misclassifies 1 point instead of 2. So arguably that green one is a better choice. So you can modify the centroid method to use off-center splits like that, but probably the smartest way to do it is just look at what gives you the best training error. So I want to go on to the first really famous linear classifier. And it's called the perceptron algorithm. It was invented by someone named Frank Rosenblatt 2/3 of a century ago, back in 1957. So it's a pretty old method. It is no longer state of the art. In particular, it's really slow. But it is a correct method for linearly separable points. It always finds a correct linear classifier that gets 100% training accuracy on linearly separable points. Now again, it's obsolete, but the reason we want to take a brief look at it is because, not only because it's historically interesting, but also because it gives us a first easy look at basic ideas of how do I use optimization algorithms to find a linear classifier. So the perceptron algorithm uses a numerical optimization algorithm. And that algorithm is one that we're going to revisit often this semester. We'll use it over and over again in different contexts. It's called gradient descent. And gradient descent is most of the calculus you need to understand for this course. All right, so I just want to do a quick poll, get a sense of familiarity with certain things. How many of you already know what gradient descent is? Okay, about half of you, I guess. How many of you know what a linear program is? Oh, almost as many. And how many of you know what a quadratic program is? Okay. We are going to learn what most of these things are, if you don't already know. As machine learning people, we will be heavy users of optimization algorithms, including things like the simplex method for linear programming. But unfortunately, in this class, I don't have a lot of time to teach you algorithms for optimization. We will learn a few, mainly gradient descent algorithms, but if you really want to learn more, I highly recommend taking EECS 127. Coming back to the perceptron algorithm, let's suppose that we have n sample points as our input. We're going to call them capital X1, capital X2, and so on up to capital Xn. And the reason I'm using a capital X here is because we typically store these vectors as the rows of a matrix called capital X, also called the design matrix. And so when I use a subscript here, I'm picking out a specific row of X, representing a specific sample point. But then just to confuse you, I'm going to assume it from when I pick it out, it becomes a column vector. So all those X1, X2, and so on, assume that they are column vectors. In addition to being given the sample points, I am also given as input a label for each sample point. And those labels are called yi. For sample point xi, its label is yi. And that label can only be 1 or -1. It will be 1 if sample point xi is in class C. And it will be -1 if sample point xi isn't in class C. All right, so let's generate a machine learning algorithm that uses optimization to try to learn all of these training points and labels so that it assigns the correct label to every input point. Now, to make the presentation of the perceptron algorithm simple, it really helps if we make a simplifying assumption right now, which is that we're going to consider only decision boundaries that pass through the origin. And I want to be clear that, well, the fact that it passes through the origin means alpha is 0, okay? You might ask, is this a bad limitation? And the answer is, yeah, in practice it usually is a pretty bad limitation, not really acceptable. But on Wednesday, I'll show you a magic trick that completely resolves the problem and brings back general decision boundaries that don't necessarily pass through the origin. So just suspend your disbelief for now, and remember, I promised you we'll fix this on Wednesday. With that in mind, now that we've decided that we can drop alpha and just have our decision function be w dot x, that's the whole decision function. Now our goal is to find the weights that will make this all work out. The weight vector w such that for sample point xi, its inner product with the weight vector w is positive, or at least not negative, if it has a label of 1, if it is in class C. And we want that sample point I, if it's not in class C, then its inner product with w will be less than or equal to 0. So again, remember that in this context, xi dot w is the signed distance of the sample point from the decision boundary, because we've set alpha to 0. So you'll notice I have two different conditions. The first condition applies to points in class C. The second condition applies to points not in class C. We can actually simplify this a little bit with just by and write both of these constraints as a single constraint with a little trick. You can just multiply yi by xi, and then we always want to satisfy the constraint that yi times xi inner product with w is non-negative. And that holds for every sample point. So we are trying to find a value of w, the weights, that satisfies all of these inequalities, one for each sample point. These inequalities are called constraints. They are constraints of the optimization problem that we want to solve. All right, how are we going to get this? How are we going to find a w that has all these magic powers of making all these inequalities happy? Well, here's an idea. We define a risk function that we'll call r, which basically tells us how badly we're doing at the moment. And so the idea is that r is positive if some constraint is violated. Whereas it has a value of 0 if every constraint is satisfied. Then we use optimization to choose a w that minimizes r. And that is how we train a perceptron classifier. So how am I going to define this risk function? First, I will define a loss function. There will be one loss function for each training point. And then the risk function will just be the average of all the loss functions. So the loss function, which you can also think of as the risk for a single training point, is usually a capital L. It takes two endpoints. Z is the prediction made by my classifier. Yi is the label that I've been given as input associated with sample point I. And so the idea of the loss function is that we're going to set it to be 0 if we have predicted correctly, which means that the prediction times the correct label has non-negative sign, or to put it another way, yi and z probably have the same sign. But if the prediction is wrong, if the signs don't agree, if the prediction is negative and the label is positive, or vice versa, then we are going to have a loss of minus yi times z. And I know there's a minus sign there, but this is always going to be positive. The minus yi times z, we only score that if yi and z have opposite signs. So that's always going to be a positive loss if our prediction is wrong. All right, so just to reprise, if z has the same sign as yi, then the loss function is 0, and that means that we are happy. That's what we want. But if our prediction has the wrong sign, then the loss function is positive. And we are unhappy, and we want to fix that. So, in a sense, for each training point, we're trying to squeeze down its loss function to 0, or at least as close to 0 as possible. All right, so now that I've defined the loss function, the risk function is going to be the average loss over all the training points. Now, for the sake of optimization, we can also call this function our objective function or our cost function. Those are not perfect synonyms for risk function. Risk function has some additional baggage. Risk is always an average loss, whereas objective function and cost function just refer to anything you want to optimize. But in this case, the average loss is what we want to optimize. So the risk function is the average of all the loss functions, that is one loss function for each training point. And so if you can get all the loss functions down to 0, then you get the risk function down to 0. That's our goal. Let's substitute in the value of L that I wrote above. So that's just minus yixi dot w. I've made one other change here, though. I'm acknowledging the fact that for correctly classified points, the loss will be 0. So I only need to look at the points that are incorrectly classified when I compute this sum. So V, this capital V here, is just the set of indices. We answer the question, for what values of I is it true that the point is misclassified? Or, in other words, we have failed to satisfy the constraint. Because remember, we want this constraint, or I guess it's further up. We want this constraint. We're trying to satisfy this constraint. So in the case where that constraint is not satisfied, that's where we will have a positive loss function for that sample point. All right, so if W classifies all of the training points correctly, then the risk function will be 0.